right, let's make predictions now with model. All right, so let's say we select our model, it passed all the tests, now it's time to make them useful. All right, so the way we make them useful is first, we need to, so let's say we're using them to forecast, right, so to predict. Then the first thing I need to do is predict the X variables, right? Let's say we're doing a yearly prediction, like, okay, GDP for next year. And if GDP is a function of population and, let's say, unemployment rate, to keep it simple, right? If you want to predict the GDP for next year, first you need to predict the unemployment rate and the population for next year, right? So, you might think it's a little silly at this point, because why not just predict Y in the first place, if you have to make two predictions to make another one, right? So I guess the idea is that predicting population is a lot easier than predicting GDP, right? But yeah, you got a point there. Okay, and the prediction for the X values are going to be the vector X naught. So the 0, it means that these are new values of the variables X. So in the example I just gave is the value of unemployment and population for next year. Now, it doesn't have to be a forecast of unseen values. It could be a forecast within the sample, right? You want to make a prediction of what would have happened, let's say, last year. You can also apply it for previous year. Anyway, so the first thing we need to do is predict or set up the X naught vector, which is the vector of X variables for which we want to know the predicted value of Y. All right. Now, there's two types of predictions. First is the prediction of the mean response. And the mean response is simply the regression line, is the mean of Y given X naught, which is the regression line again. All right, so X naught times beta is your regression line. Okay, so that's simply our prediction, right? So we have, and now, yeah, these are hyperplanes and whatnot, but just to illustrate, so this is X, and then there should be X naught. X naught is a particular value here, right? So we want to predict this value in this section. Now in the next section, we're going to predict any value according to the distribution of Y. But in this section, we're just going to do it for the mean. All right. So that's your equation for the prediction. Very simple. Just apply the line. So you plug in the values of X and your line of. All right. Okay. But then we also would like to have a confidence interval, right? Not myself, because I don't believe in them, but in general, people like these. Okay, this is a typo. It should be the covariance matrix of the betas. Anyway, all right. So you see here that Y naught is a linear combination, right, of the betas, because the betas are the random variables now. And the X naughts, they're just constants, right? So it's the betas that are random variable. They're normally distributed, remember? And they have a covariance matrix C of beta like that. Okay? All right. So given that, that's the mean and that's their variance. Okay? And in terms of the matrix A that we defined before, it would be this. Bottom line, we know the mean and the variance, and therefore we can perform the t-statistic, right? which is the estimated value of this point, minus the true point, which you never know, but it doesn't matter, divided by the standard error of this estimate of y naught right here. Okay, and so you can do hypothesis test about that predicted value, right? Or you can do the confidence interval, right? And it's the same formula as before. So it's the mean value plus or minus the t-statistic with n minus p minus 1 degrees of freedom times the standard deviation of the prediction. Now all this is in vector notation, but it should be doable either in calculators or, yeah, not by hand though, okay? So, and make sure you know how to multiply matrices and all that. Right. Now, a particular realization. So here's the other picture I was telling you about. So you have the x and y and x naught somewhere here. And so previous section, we predicted that point. Now, when we say particular realization, we mean that it could be any point in this vertical line drawn from a distribution that it's normally distributed, right? This one. Normally distributed with the mean given by the regression line and sigma square as the variance. And that's, okay, so at this point we're going to make a prediction drawing from this distribution of y naught. Right? And it's just because y naught is the regression line plus the error term, and that error term is assumed to be normal 0 sigma square, right? Okay, so here we're going to proceed in this way. We're going to note that the particular value minus the line, right, okay, is normally distributed with 0 mean because both have the same expected value, right? Y naught has this expected value and y naught hat, we saw it before, has the same expected value. Where'd it go? Oh, right here. Okay. So mean 0. And then the variance, so it's going to be the variance of, there's a sum of two random variables. So and they're independent, okay? That's why we simply add the variances. And this should be capital Y naught. All right, the variance of Y naught hat, we discussed it in the previous section. And here the variance of Y naught is sigma squared by this, right? That's the assumption of linear regression models, right? Is that, yeah, their values are, the mean of the values is the regression line, and then the variance is always sigma squared. So that's why the variance of Y naught here is sigma squared. All right, and the second term is the variance of the regression line, which, yeah, we saw in the last section, okay? So we're going to have this 1 plus term arise here. And if you compare this equation with this one, that's the only difference, right? So here there's not the 1 plus, but here there is the 1 plus, right? And that 1 plus, yeah, it comes from this added variance, right? So this makes a lot of sense. Before we predicted this value on the line, so E of y given x naught, okay? All right, and then let's say near this point, you're going to draw the particular value, which let's say is this one, right? And this one has an extra variance of sigma square. Okay, so that's why it appears here in the 1 plus. All right, 7 degrees of freedom. So we can perform the same confidence intervals or hypothesis test. Same type of formula. Very good. Now we're going to do examples of this in class. For now, let me talk a few more minutes, 3 more minutes, about simple linear regression. Okay. So in this section, we're going to look more closely at the formulas that we get for the case where we have a single random variable x. Okay, so our matrix X now is just with a single explanatory variable. Okay, and in this case, things simplify a lot. So you see, this is the vector A we defined before. Now it's a lot more manageable. Having to do it by hand. Okay. Now we're going to need to define extra variables, the s-axis. These three, okay? So yeah, take a look at their definitions. They're related to the variances, or the sample variances in this way, right? That's for sxx, syy. And sxy is related to the covariance. Alright? So yeah, those are all values you can compute with the data. And the second lines here are the shortcut formulas which are really useful. Okay? So make sure that's... Oh yeah, so this section, you could... I'm going to give you guys the handout so you can have it handy for your test. Alright, so no need to write down your sheets, all these formulas. Alright. So, yeah, these are the formulas for beta now, a lot simpler, beta 1 and beta naught, okay? So you can do it by hand with very simple formulas. Same thing for the variances, so we have all the formulas now for all the parameters. Beta naught, beta 1, and sigma squared, which is all you need really, alright? Now the test for significance, the same as before. Now it has this formula in terms of the sxx values. Okay? This is a good thing to know. When you have a linear model, could be with more variables, not just one x, but it turns out that they always go through the mean. So that's the mean of x, and that's the mean of y. Alright? Alright, and yeah, this is another derivation of the beta coefficients, taking derivatives again, but now we can do it in scalar form and not in matrix form. Okay? And here you see why the r square is close to the correlation coefficient, just by applying the formulas again. So first the definitions and then the formulas, the approximation. Okay. So it's really a summary of all the formulas we've already seen, but in simpler form. All right. Now this is important. It tells you that the slope of the line, okay, is related, so it's proportional to the correlation between y and x, right? And the factor is the ratio of, those are the sample standard deviations, right? So beta and the correlation coefficient are really, so it's a constant times, let me just say c times. They're very related like that, okay? So when you're testing for beta equal to 0, you're also testing rho equal to 0, okay? So that's another reason why that beta test is so important. The t-stat and everything, okay? But yeah, making predictions is just applying the formulas we saw in this case. So here we have simpler formulas. So these are the ones that I might ask you on a test. Maybe not with the multiplying matrices and everything, although you could do it like that if you wish. Right? So again, same simpler versions of the formulas that we already saw. Alright, let me show you a formula that I forgot to emphasize, which is up here. So it's regarding the variance of beta 1. Alright, yeah, this one right here. Alright, so that's your formula. The important thing here is that it's divided by SXX. Now, if you recall, SXX is related to the sample variance, right? It was n minus 1 s squared of x. Now, s squared of x is our sample variance we define in chapters 5 or so. Okay, so it's very related to the variance of x. That's the point, right? Now, you see that the variance of beta now remember, beta 1 is the slope of the line, right? So the variance of the slope of the line is an indication of how reliable your model is, right? You want a low variance, right? You want to minimize risks. And that's considered in the t-statistic. That's why we do that, the t-statistic, okay? But from this formula, you can gain some insight that you didn't before. So in a way, the variance of beta is a constant, right, which is given by the formulas, divided by the variance of x, kind of. Okay, which means that if the variables x are very spread out, you know, like if the data were like this, so reasonably well spread out, so you would obtain a lower variance of beta 1, which is good. But if the data were not spread out, put it in red, it's like if the data were all clumped together in a little area like that, you see, so the range of that x is very small, so the variance would be very small. Okay, the variance of beta 1 would be large, because you see, when the variance of x is really small, it looks probably like a big dot of points, right? And you can fit any line by a single point, right? Now, it's not a single point, but it's to give the idea, right, the relationship between the variance of x, so the scatter in the x-axis, and the result for the variance of beta 1. All right, yeah, so that's what I wanted to show you here. Now, let's go back and do some examples. All right. All right, so let's do this one. Let's say you have this amount of data given to you. So just the x and the y's, okay? So in this case, y is the annual number of divorces, and x is the time. Okay, that's your data you have. Then the way to apply the formulas here. So we want to get, we want to calculate all the s's, because once you have the s's, well, and the averages, right, and the sample size. Once you have all these, then you can estimate the parameters of your linear model, which are, yeah, the betas, but also you want to calculate the sigma square, right, and the coefficient of determination, r square. All right, so the first step would be to calculate the product of x and y and the squares, so that then you can have the sums right here. Okay, and with these sums are the ones needed to calculate these guys, right? So pretty straightforward. Okay, Yeah, and then you find the beta. It's always a good idea to plot the line, right? And we always do the test statistic to make sure it's a good variable. In this case, yeah, 5 is a lot larger than 2, so it's a good model, right? So very simple example, just calculating the basic information. Okay. All right. Let's take a look at this type of examples. All right. So Y now is the city mileage, mile per gallon of a car, and X would be its weight. All right. Now, in this case, what I will give you would be the data summary. And then you have to come up with this table, right? Which is the same as before. Now, this is a little easier because I already give you the sum of the xi, yi's and the sum of the squares, right? It's like I already give you this column, so to speak. Well, these three, right? So that it's easier to calculate what you need to come up with this table, right? Yeah, beta, alpha and beta. So alpha should be beta naught. Yeah, and beta is beta 1. Okay. And yeah, also give you the residuals and normal probability plot. Okay. And then here is assess the model if you think it's good or bad, right? Maybe make predictions. Here we're showing the confidence intervals for a single prediction and for the mean response. Okay, mean response, yeah, wait. Single prediction, I think we call it particular predictions, yeah. Of a particular realization, we call it. So this would be, right? And you see that the confidence interval or band, really, right, for the mean response, it's a lot narrower than the prediction for a single prediction or a particular realization, the gray one, right? And it's because of the added variance due to the particular prediction thing, the 1 plus, right? So yeah, the gray is always greater than the orange, which makes sense, right? Okay. Typically, yeah, the slope, we see a very negative slope, right? And we need to see if it makes sense. Probably does, right? So the heavier the car, yeah, the less efficient it is. So the less the mileage you get. So beta 1 being negative makes sense, right? And then what you want to do is calculate the t statistic for the beta 1. Okay, so the residual plots, yeah, I can see a nonlinearity, right? There's kind of a pattern like that, which you can see in the data as well. So what it's saying that probably we should fit a model with a quadratic term because it's nonlinear. So the residuals are not good in this plot. The normal plot is pretty good. It's pretty straight. So I'm happy with that. Yeah, but the problem with this model would be then the residuals. Let's click on this, more examples here. There should be a good collection of examples. Alright, so these are the other examples after clicking the link. Yeah, so if you scroll down, there's a bunch of them. You can practice. All right, let me see. Yeah, there's probably too many, right? But anyway, it's good to have more than fewer. All right. So yeah, let me pick any other random one that that looks okay. Yeah, they're all not so good, right? Anyway, let me choose that one. Yeah, so in these ones, all right, so these don't give you the data, they just give you the model outputs. So this is another type of example, right? Where you don't have any calculation to do, just assess the model. All right. So, okay, this is values of homes versus the average number of rooms. Right, so the more rooms, the higher the price. So yeah, the slope should be positive, which is the case. Oops, what did I do? Right, so the slope is, yeah, for some reason I can't annotate, so hopefully you can see the mouse. The slope is positive, right? Well, we see it from the graph. That's good. They give you the t-statistics, right? So the beta 1 is greater than 2, that's great. Oh, I haven't said anything about the t-stat of beta naught, the intercept. We don't care about the intercept, okay? Because it really doesn't tell you much. Beta 1 is the important one because if it's 0, it means that there's no relationship between x and y. So might as well drop that variable. But yeah, we don't care if the intercept is 0 or not. All right, and r squared is 0.48, so it's kind of in the limit there. Yeah, residuals are not very good, right? The variance, it starts small, but then it grows, and the normal probability plots are not good either. It's probably too much error in the tails. All right, yeah, it's pretty bad normal probability plot here. All right, this one I'm liking the residuals, no apparent pattern. No probability plot, however, it's has way too much error at the end there. Let's keep going. Yeah, here also the variance increases and the residuals, right? So, and normal probability plot is not very good either. Same thing here. Now, yeah, these are a lot fewer data points, you see, and these are fatalities. Yeah, these are safety variables in Georgia, I believe. Yeah. So here are the ones where we might give you the data summary like this, and you would have to obtain all the other parameters, okay? And also the t-statistics and everything. With so few points, it's hard to evaluate the residual plot, right? I mean, you can always see a pattern with few points, but yeah, this one's particularly apparent. Right? This one looks better. Yeah, so here we have a lot of stuff to practice. All right, let's look at other problems here we have in the textbook. So I just click on this link that follows this example, all right? Now I had to copy and paste the link because by clicking it didn't work for some reason. Hopefully it works for you guys. If not, let me know, please. Okay, that's another format of examples where we give you the sums already, so it's easier to compute everything. Okay, so find the regression model, the hypothesis test, and all right, so let's go through this one. All right, so first we do all our calculations right here. They're spelled out for you. So we get all the coefficients and everything we need to. All right, so part A, that's the regression line. The beta being negative doesn't make sense. Let's see. Right, so what is y and what is x here? All right, So we record the speeds. So y is the speed in miles per hour, and x is the rainfall at the time. Okay, so yeah, we expect the negative slope, right? Because the more the rain, the slower you should go. Okay. And then the t-stat for the beta 1, right? This is, we can call it t of beta 1 hat, right? That's a formula, right? It's greater than 2, so it's good. No, wait. No, it's 5, so it's greater than 2. Yeah, here we calculated the exact value from distribution, but yeah, at this point I'm happy with just comparing it with 2. Unless you really have low sample size. All right, here we're making a prediction of let's see. Such whether or not the average speed is how we exceed the speed limit on non-rainy days. Okay, now the speed limit is 65, so you want to see if in non-rainy days this is greater than 65, right? That's the alternative hypothesis. Okay, now non-rainy day means x equals 0, so it's just beta, right? We're testing for beta in this case, and that's going to be your usual hypothesis test, right? We know everything about beta. We know the variance and we know the value, and yeah, you know the t-test, the t statistics for beta naught, right? It's always the same, right? Is your estimation minus the beta naught that you're testing, in this case 65, divided by standard deviation of your estimator. Right, that's 2, so it's right in the verge, right? It's equal to the t-statistic to the critical value. So this is an example where you cannot make a call really clear, right? Because 196 is too close to 2. Now, going by the book, we would have to accept h naught, right? Because it's less. But here I would add a sentence saying that the difference between these two numbers really gives the impression that our conclusion is weak, right? We're not. And the thing you want to do is collect more sample, right? Collect more data to make sure these results are significant. All right, and part D is computer confidence interval with the value of x naught equal to the average, which is 78, right? And that's just the formula. And again, we know everything here, so that's your confidence interval. Now, how to interpret? Go back to chapter 6, I think it was, right? And you'll see that it makes no sense. Anyway. Yeah, so that would be the interpretation, right? And make sure you understand why you cannot say that. All right, and finally we do a confidence, this would be a hypothesis testing for the variance, which is very similar to the one we did in chapter 6, all right? So I would let you guys look at that. All right, and then F, what was F? Estimated probability that an individual driver will be traveling at 10 miles over the speed limit. Okay. So we need the probability of a particular realization, right, which has this variance, right, with the 1 plus. That's the key of this question, right? Because that's the mean, right, 53. But what is the variance? The variance of a particular realization is this one. Okay, now if the question, and then you just calculate probability with the normal distribution. If the question were instead of particular, like individual driver, if it said probably that an average driver, right? So let's do part G here. Estimate the probability that an average driver will be traveling, right? Now, when it's average, it means it's the regression line. So in that case, basically, this one, the only change is that this one disappears. Oh, damn it. There you go. So just delete it from that formula. And that's the variance of the mean value, right? If you're not sure, please go to sections 7.8.1 or 7.8.2 to see the difference between prediction of the mean response or predictions of a particular value. All right, so yeah, you're going to get a different number here, so everything else will be different, but that's the only change you need to make. All right, so at the end of the chapter, we made it. End of the book, actually. There's more problems for you to practice, okay? And they're very similar to the ones I showed you on that website where you clicked. Okay, so if you have time, it would be a good idea to go through these. All right, yeah, we saw these. Alrighty, see you guys in class.